Okay, so we continue for question 5.25. So it is actually to reflect the effect of surface roughness on flat plate and on our object here. So let's say we have an air at 20 degrees Celsius and 1 atm flows at U equal 12 meter per second past a smooth flat plate. It is desired to trip the boundary layer to turbulence by stretching a 1 millimeter diameter wire across the plate at the wall, where will transition occur if the wire is placed at x equal 1 meter. So what wire location x will cause the earliest transition? So the idea of this one is actually we have a situation like this one. So and then when we put a disturbance, so the laminar flow will turn into turbulence. But in our first question, we are calculating about the instability. So means that if the wire placed very at the beginning here at early stage, might be it cannot change a laminar flow into turbulence. So means because the laminar flow is still stable on that time, you give some disturbance, but laminar flow will come back to its previous condition. Means it will go back to the laminar condition. So the question here, so if the wire is located at 1 meter here, so the distance from here to here is 1 meter. So where will the transition occur if the wire is placed at 1 meter? And then the next question is what the wire location X will cause the earliest transition. So the earliest transition here means at the borderline of the stability. The first instability occur. Okay, so you could read this from the textbook. So the idea is, okay, first we need to determine the location of x equal 1 meter here. So we could take kinematic viscosity of this one, depend on the temperature and the atmospheric pressure there. So so we could substitute in these Reynolds numbers. So we could get it is 8 times 10 by the power of 5. So we assume, let's say, as we assume that this is still a laminar boundary layer. So it is quite difficult actually to define whether it is laminar or turbulent, because normally people will take 5 times 10 by the power of 5. So let's say we take 1 times 10 by the power of 6 to be the transition between laminar and turbulent. Okay, let's say the surface is smooth. So and then Reynolds number 8 times 10 by the power of 5 is still a laminar boundary layer. So and then because it is laminar boundary layers and we don't know the velocity distribution, the U over U we don't know, so we just take a Blasius solution as our representative solution. So from the Blasius exact solution, we could get the equation for delta star here is 1.72x over Reynolds number. We substitute the value of x here with the 1 meter here, so we could get it is 1.923 millimeters. So and then from the question, we know that the wire diameter is K is equal to 1 millimeter, and we could calculate the ratio of K over delta star as 0.52. So why we need to calculate this ratio? Because we are depends on these ideas. So let's say from the textbook in figure 5.3, there is one research comparing the location of wire, a trip wire on flat surface and so on and so forth. So finally they come with this graph. So this is a flat plate, two-dimensional roughness transition data normalized to eliminate free stream turbulent effect for incompressible and also for the compressible. So we neglect the compressible one because we assume that we are just focusing on incompressible. Because for compressible, we need to play around with the Mach number here. So it is another big story because normally compressible mean we change the density. So we change the density. It can be occur at two conditions. One is at higher pressure, and one at the high velocity. So normally, okay, people will start play around with the high number of velocity. So when you are conducting experiment with high velocity, so you would change your terms of velocity into Mach number. So we neglect about Mach number here. So mean we are focusing on this one. So and then we have from this graph, so for the x-axis here, we have a ratio of k over delta star, and then we have the Reynolds number rough divided over Reynolds number smooth. So according to our previous calculation, we found that the k over delta star is 0.52. So let's say we take the value of 0.52 is here. So and then we could take estimate the value of the ratio of Reynolds number rough over Reynolds number smooth is equal to 0.4. So let's say, so and then at zero turbulence, so means at normal condition, we assume that for a smooth one, the transition is occur at 3 times 10 by the power of 6. So this is actually referred to figure 5.33. So and then we could calculate the Reynolds number of rough by using this equation. So this is actually the ratio of these terms. Okay, because the value of smooth one is given from another table. So we could substitute the equation here, and then we could get the Reynolds number for the rough one here. So and then because the smooth one is already given, so we could get the Reynolds number for the rough one. So and then we know that the equation for the Reynolds number is ux over nu. And then if we know the Reynolds number here by this calculation, so if we know the Reynolds number here, so means that we could calculate the value of x. So and then the value of x will comes out as 1.5 meter. So mean if we put a trip wire here, so this is the trip wire. If we put a trip wire here at distance of 1 millimeter, so the transition will occur at we predict it will occur at x equal 1.5 millimeters. So, okay, so this is the meaning. So and then, so we try to calculate without any wire. So for example, for the smooth plate, so the transition usually occur at 3 times 10 by the power of 6. So I think this is related to this term. Okay. So and then we just use this term. So we substitute with the Reynolds number equation. So we have ux over nu here. So we found that the x is equal to 3.75 meters. So means that without any trip wire, so the transition will naturally occur at x equal 3.75 meters. Okay, it is stated here. So and then we want to calculate what is the lowest, the soonest. Okay, we refer to the question here. So what is the location of x will cause the earliest transition? So means what is the location of our wire here to be located that the transition could occur. As I said, if we put too early, so might be the laminar boundary layer is still in their stable region. So the laminar boundary layer will back into will maintain in a laminar boundary layer. So the transition maybe not occur according to what we want. So to solve this one, okay, we go back to the this figure actually. So I enlarge the figure like this one. So because we want to get the earliest value. So we need to get the lowest ratio of Reynolds number for rough and Reynolds number of smooth. So according to this graph, based on what it could give us here, so the value, the lowest value is 0.1, and then if we get this value, it is occur at ratio K over delta star equals 0.8. So and then we know that the ratio is 0.1. So and then we know that the Reynolds number smooth is 3 times 10 by the power of 6. So and then we could calculate the value of rough Reynolds number, which is 3 times 10 by the power of 5. So and then this is just from the you could compare with the let's say this is the equation from the textbook. So you have the K over delta star is equal to 0.8. So it is equal to K square root Reynolds number for rough divided by 1.72x. So the x here is equal to 398K. So if the K is the wire diameter, so let's say the diode diameter is 0.001 meter because it gives us as 1 millimeters. So the X is 0.398 meters. So and then the here is actually come from if you substitute the value of a delta star here. So and then the 1 millimeter wire means that if we place the 1 millimeter wire at x equals 0.398 meters, so it will cause transition almost immediately downstream. Then, so we go for question 5.26. So we repeat the problem 5.25, means we have a trip wire here. Okay, so what happened if the free stream velocity here has 1% of turbulent level? So I mean it is not start with a very good flow, not steady and uniform flow. So it have it has a turbulence element there. So let's say we calculate the value. So if we calculate it as ux over nu 8 times 10 by the power of 5. So because we have it is turbulence here, so we make it this level is turbulence. So it is okay actually if you don't calculate this one. Okay, let's say the turbulent fraction is 0.01, so which is 1%. So and then we use the Van Dries and Blammer equation. So we have this equation, so we substitute the value of t here. So we found that the Reynolds transition is actually occur at 5 times 10 by the power of 5. So means that the location of trip wire is actually too late, because if your free stream velocity has element of turbulence, so means the transition will occur earlier, and then according to this calculation, the transition mean the changes from laminar to turbulent is occur at 5 times 10 by the power of 5. So mean the location of your 1 meter, location of x equal 1 meter for your trip wire is actually too late, because according to our calculation previously here, okay, we substitute in the Reynolds number. So our Reynolds number, by substituting the value of x here is equal to 1 meter. So we will get 8 times 10 by the power of 5. So means that the location of that one is already turbulent. Now we are discussing about 5.28. Repeat problem 5.19. If the free stream has turbulent level of 4%, find the estimated transition Reynolds number by two different methods and compare. So this is the question for 5.19. So air is 20 degrees Celsius, 1 atm, flow quietly toward a wedge of half angle, 36 degree. Now we have the angle of wedge, half angle, So and then resulting in a free stream, power law free stream, and a laminar boundary layer along the surface. Use Wasan method to estimate the transition Reynolds number. So from the previous problem, we know that U is equal K X by the power of 1 over 4, beta is 0.4, and lambda is 0.05. So, and then we know that lambda is greater than 0.04, so we cannot use Dunham estimation, because Dunham estimation is only valid for lambda less than 0.04. So what we could use is, we could use the Schmidt and Henningsen equation 5.47. So the equation is written like this one, and the T here is showing the percentage of the free stream turbulence. So, but in unit of percent. So if we have 4%, we need to substitute the value of T equal 4 here. In this equation, then we could calculate the value of Reynolds number here. It is between 90,000 to 122,000. So the number is quite different in the big range, but normally we could assume that transition can be occur is around 1 times 10 by the power of 5.